Yeah, welcome everybody to the last UW Robotics Colloquium of the winter quarter. It's my really great pleasure to introduce Oliver Krömer, today's speaker. He is faculty at Carnegie Mellon University in the Robotics Institute, where he's leading the Intelligent Autonomous Manipulation Lab. Oliver got his PhD from both kind of Max Planck Institute and TU Darmstadt, where he's working with Jan Peters. And for his PhD thesis, he was awarded a finalist of the best PhD thesis in Europe of that year. So he's already doing the PhD on some really excellent work. After the PhD, he spent two and a half years at USC working in Gaurav Sukhatme's lab. And Oliver is doing some really fantastic work in machine learning for robot manipulation, where also, of course, coming from Jan Peters' background, he does both the low-level control aspects of manipulation. So you might have seen some of his really exceptional work on kind of cutting vegetables and things like that. But beyond just looking at the more lower level kind of control learning aspects, he's also really focusing a lot of his efforts on understanding how these low levels connect to the higher level, longer term manipulation tasks, where it's not just a single, let's say, control policy you want to learn, but you want to see how you can break down these really complex manipulation tasks into subcomponents and into skills. And that is what he's going to talk to us about today. So I'm really looking forward to this. Thanks for joining, Oliver.
Oh, thank you for having me, Dieter, and thank you all for joining. It's an absolute pleasure to be presenting here. As Dieter mentioned, I'm Oliver Krömer, and today I'm going to be presenting some of the recent work from my lab, the Intelligent Autonomous Manipulation Lab at CMU. And I'm going to be talking about structuring manipulation tasks for more efficient learning. So in the future, we want robots to perform a wide range of different tasks. We want robots that can help us with cooking, cleaning up our houses, taking care of the elderly, working in agile industry. And as we sort of, want to increase this domain, the set of domains that these robots can work in, it's really a challenge about bringing robots into unstructured environments and being able to adapt autonomously to new situations. And so in order to increase the range of applications where we can use robots, in particular robot manipulation, we really need to be looking at ways of acquiring robust and versatile manipulation skills. So skills that can generalize to different situations, different objects, different scenarios, but also that can be performed reliably, that are checking for errors as they go along, and that can recover from problems as they arise. Okay. So how do we do that? So really, we want to consider a complicated environment such as a cooking robot, right? So here we have a robot is preparing a meal. There's various objects in this environment, various tasks it needs to do. And the first thing we really want to think about is how can we sort of reduce the scope of that problem, right? So we have a lot of objects, but really we just want to focus on a small set of objects that are going to be relevant for the given task. We also want to focus our learning efforts on tasks that are actually going to be challenging, where we need the learning. So a lot of things we can do with planning, but for example, cutting vegetables, there's a lot of complicated interactions there where we really are better off using model-free sort of learning rather than planning. Another way that we can sort of look at this is to break it down in terms of modularity, right? So we have the small scope, but we also have a bunch of objects in there. We want to sort of identify what those objects are, which of these can we replace with each other. We're also going to be talking a little bit about modularity at the skill level. So often we can break down skills into sort of smaller controllers and how we can sort of combine those together in an efficient manner in order to perform different tasks. The last thing I'm going to talk about is interactions. So the fact that the robot is an embodied agent, it can interact with its environment. This is going to provide a huge resource of information that we can use in order to perform various manipulation tasks and gather additional information. So in this case, with the cutting robot, we have here some bell peppers, but we may also have something that looks like a bell pepper, but once we interact with it, once we learn to recognize these kind of objects, we might realize that this is actually just a toy bell pepper, which is made of plastic and therefore not actually suitable for this cutting task. All right, so to begin with, we're going to be looking at the modularity component and sort of how we can break down these very complicated tasks into smaller ones where we can sort of exchange different components much more easily without, in a robust manner. So modularity, how to break down the problem. Modularity is obviously very common in robot manipulation. I like to think about objects as a sort of a hierarchy where we have the objects at the top. We can have various different parts of those objects. We can break those down further into points. We can have features at the different levels. We can have sensor inputs at the different level. Often if we want to generalize between different objects, it's better to do this at the part level rather than the objects as a whole. This provides a lot of modularity, this ability to decompose objects into parts. Similarly, if we're thinking about sort of control and learning policies, we can also think about the hierarchy of options, right? So if we want to make a sandwich, we're generally not going to have this as one monolithic policy, but rather we're going to break this down into multiple options that the robot can choose from. So slice, cutting a piece of cheese, placing a slice of bread on top of the sandwich at the end. Each of these can be further broken down into modular parts. So, grasping is going to be something that happens very often in each of these kind of skills. And so what we want to do is we want to make sure that, we have that modularity between different options so we can, again, decompose and put together. Now, with these options hierarchies, we often think about these as sort of a sequential set of actions, right? So, well, first we take a slice of cheese, and then at the end, we'll actually place that slice. But what we want to focus on is how we can actually decompose skills into modular controllers that are running in parallel. Right? So if you think about manipulation tasks, they often consist of multiple parallel subtasks. So here, for example, we have a human placing a screwdriver for a screwing task. This involves getting the tip of the screwdriver close to the screw and also aligning the screwdriver with the axis of the screw. Once we're actually, in contact with it, we might switch over to another option, but this one can also be broken down into multiple controllers. So we have the need to be actually pushing against the surface. Again, we have the alignment. So some of these, subtasks can be shared, and we have the actual rotating of the screwdriver in order to drive the screw in, right? A couple of important points to note here is that these sort of controllers that we're using here, these are very object-centric. So if we had a screw in a different orientation, so rather than screwing sideways, we might be screwing downwards. In that case, we still want those controllers to be aligned with those objects that we're interacting with. We're also going to have sort of various kinds of controllers. So it's not always going to be force control, it might not always position, it might be some impedance. We may even incorporate some DMPs. Along some of these axes. And so we need to be able to, consider different kinds of controllers for different object-centric axes. We also want to be able to share some of these controllers between different tasks. So obviously, screwing in a screw is not the only time that we're going to have a pushing action. Pushing on surfaces is going to be a very common type of controller. And so, we can sort of acquire these different subtask controllers and share them up between different kinds of skills. Okay, so one of the key ideas of this project was to look at sort of decomposing skills, or more really composing skills from single axis object-centric controllers, right? And learning then to select multiple controllers to compose these skills. So how can we do this composition? So let's imagine we have a robot shown here as a green square. So it's going to be, it's effectively a square that we can move around. We have an object in this environment. This is this red block here. And we have a library of different controllers. So for example, here we have a force control trying to move sort of towards the center of this object. We could have a position controller moving to the center of this wall structure here, or to this floor structure here. Or we have another position controller moving to the top surface, right? And so what we want to do is we want to have a robot actually learn a policy which is going to be selecting between these different kinds of controllers and combining them together in a hierarchical manner, right? So to do that, what we're going to have to do is we're going to have to choose multiple of these primitive controllers in a prioritized manner. So for example, we could say that the highest priority is to push against the object, and then the second highest priority, or the 1th priority, is to actually move the object close to the top of this corner. And so we want to combine this force controller with this position controller. And we can do this with hierarchical control, where we project the sort of lower priority controller, so the 1th controller here, into the null space of this force controller, okay? And so we'll get a behavior like this, where we now have force control in one direction, and at the same time, we're trying to achieve this additional task of moving the block up to this corner point. We can do something very similar for rotations. So in rotations, we often want to align certain axes. So if we want to, for example, grasp this door handle structure here, we can define different axes on the door handle and on the gripper, and we can have individual controllers for aligning the green one with the different green ones, the blue ones with different blue ones, and the red ones with different red ones. And then again, we need to select a subset of these in a prioritized manner. So here, for example, we choose to align the blue one with this blue one, and this green axis with this green axis. And again, we have priority here. So we always want to make sure that the alignment between the blue ones comes first. And then sort of in the remaining plane of rotation around that axis, we can also try to align the green controller, okay? And so if we combine these, we'll get a behavior that's going to align both the blue and the green with the desired axes. So we can create, again, a sort of combined skill there. The question then comes, how do we actually select between these different controllers in a prioritized manner, right? So we can sort of create this set of axis controller that at every time are going to propose a kind of an action for the robot to perform. We want to select from those and then combine them together to get this sort of hierarchical skill, which will then perform the task. And the choice of controllers is going to depend on our current state. If you think about the the screwdriver example, before we actually reach the screw, we want to be able to use the alignment and reaching behaviors together. Whereas once we're actually in contact, we want to maybe switch over to force control and also incorporate that rotation behavior. So if we do this sort of in the naive way, we can sort of take however many controllers we have, we can take all different combinations of those, and we can generate a large number of different actions. So if we have 3 controllers that we're trying to choose from a set of 20, we're already going to get 6,840 different combinations or potential skills. So obviously, trying to choose from that high number of actions is going to be fairly inefficient. And so what we really want to do is we want to see if there's a more efficient way of doing that and sort of sharing information between the controllers. So the way we do it is by defining an expanded MDP. So rather than sort of choosing all 3 of the controllers at the same time, instead what we want to do is we want to break it down into smaller parts. So first we're going to choose one controller, then the second, then the third, and then actually execute, okay? And so the controller that we choose at the first time step here, which, time step in this case is not an execute time step, it's sort of a mental time step. The first controller we choose here is going to be added to the state for the second controller that we choose, okay? And so we do this by effectively representing the different controllers in a one-hot encoding manner. So in this case, be 1 out of 20 encoding. And then with this expanded MDP, we can again use sort of value function methods to sort of share information. So we know that, these kinds of controllers are more valuable than others in the future. And so, in this way, we can kind of break down that sort of combinatorial problem into a 3-step problem. And then we can solve this using sort of an off-the-shelf approach, such as PPO. So here we can see some of the evaluations. We looked first at some sort of block world problems where we're pushing objects around, trying to get this block into the slot, or trying to push this red block up the surface onto the top. We also looked at some manipulation tasks, such as using a hex key or opening up a door, which we also evaluated on a real system shown here with the Franka robots. We tried various different kinds of approaches. So using directly learning the low-level end effector behaviors, selecting just one controller at a time, selecting the top three. So if you have a network giving you the probability over various different controllers to choose from, we just take the top three without considering the other ones. We tried the combinatoric one. So in this case, taking all the different combinations and treating them as separate actions. And then we have our two approaches with these expanded Markov decision processes, where we, again represent the choices of controllers as extended states. We tried using both a one n-hot encoding. So if we had multiple controllers, they're just adding multiple ones to that n-hot encoding, or we had n1 hot encoding. So you know exactly which controller you chose for the first step and exactly which one you chose for the second one when you're making a decision for the third. All right, so as you can see, in terms of the success rates for the different tasks, we do tend to get the highest performance using the proposed expanded MDP approach, where we're choosing one controller after the other. We can also see some of the results. So here we can see the door opening task. In this case, it is a fairly challenging task, but you can actually perform quite well using one controller at a time. And so we got fairly similar performance using just the one controller and the three combination. Doing this directly in the end effector sort of low-level control space is fairly difficult. You have a lot of bottleneck states there. And so the EE space approach didn't really learn how to perform this task. We can also see on the hex key, so we looked at generalizing between different hex tools, as you can see here. In this case, it is very important that you're performing these subtasks really in parallel. So you're pushing down, you're rotating, you're aligning. And so you can see that the gap between sort of the other approaches and our approach is much bigger in this case, where you do have these more complex parallel interactions between them.
May I ask a question, Oliver?
Sure, yes.
I'm just wondering, so if you select a subset of these controllers, how does all of this go then? Is it kind of, so your reward structure is given, but then the state transition function, is that where the selection, then the combination impacts on how you make your predictions in your MDP, and that's how you then do, it goes through value iteration, or how does this work then?
So we do have like a value function over the different states. So we are simply expanding the state representation. I mean, ultimately, it is still sort of an actor-critic approach that we're using here. So the reward function is still defined just at the execution steps. From the real-world task. So we have the same reward as also the sort of the direct low-level actions here. So we're not sort of applying additional information there. Obviously, because we do give a little bit more structure to it. In terms of we do get more efficient exploration than if we do have this sort of low-level action control. And that's obviously another benefit of this kind of approach, that you know kind of what are potentially reasonable actions in this space.
So the state, so it's discrete RL.
Yes, exactly. So the controllers are continuous, but we're sort of choosing between combinations of controllers at every time, not every time step, but every T time steps.
Thanks.
There was also I feel like a comment or something like that in the chat. Is that the hex key, were these trained in sim and then deployed on the hardware, or trained directly? So these were trained in simulation, then employed on the hardware. Yes, that's a good point. And so these, yeah, I should mention these are the training curves in simulation. All right, so we saw a little bit of modularity in terms of representing the policies of our skills. But obviously, we're not just interested in the skills themselves, but we also have to think about other things such as the preconditions. So the preconditions of a skill are all the sets of states where if we executed the skill from that state, they would result in the desired effect, right? So if we have a grasping skill, the preconditions are all the states from which we could actually grasp an object. And the preconditions, I would say, are very important because they really define the scope of the problem, right? You can have all the complexity in the world. If you can sort of define the preconditions to be very limited, then that's going to make things a lot easier for your policy, because it can learn a policy that's very specialized for those situations. One example I always like to think about is, playing table tennis with a cat on the table, right? If you've ever tried this, it's pretty much impossible, but no one would say, oh, I don't know how to play table tennis because if there's a cat on there, I can't perform it, right? Instead, our preconditions say that, the table tennis table has to be clear, then I can play table tennis and achieve the desired effect. And so part of the task of the preconditions is to take all of that complexity of the real world and be able to handle that and sort of say, okay, this is a state in which I can apply the skill, and this is one where it's not going to work, right? And so if you have lots of irrelevant objects in the scene, you also need to be able to handle that. And yeah, I'm going to avoid going into a rant about why preconditions are important. I'm hoping most of you agree with me. All right, so for this project, what we're looking at is how to actually represent the environment of multiple objects. Sometimes we can add objects, we can remove objects, we can exchange objects for different objects, and how we can sort of learn the preconditions over those various different scenarios. So the way that we did this was we took the scene and we break it down into a graph. In particular, a graph over individual objects. Although you could probably go also deeper into two parts, but at this stage we're looking at individual objects and looking at the pairwise interactions with them. So one of the key insights in this project was that even though we might have a very complicated scene, the interactions between pairs of objects are often a lot simpler than that scene overall, right? So we might have a cucumber and a knife and bell pepper, or plastic bell pepper in this case. A block here, we got multiple objects fairly close to each other, but ultimately, if we look at this, at the low level, we are going to have fairly simple interactions. Objects are next to each other, they're above each other, they're stably on top of each other. And so the question is, can we sort of learn those sort of interactions very efficiently in simulation, and then sort of using that learned representation of the pairwise interactions, can we look at the more challenging task of predicting the preconditions for the overall scenario, all right? And so it really is about taking that complexity, breaking it down to pairwise interactions, and then learning those simpler interactions first. So to do that, like I said, we worked in simulation to identify different types of interactions. Here we're always looking at pairs of objects. We have different geometries, and what we can do in simulation is we can actually perturb these objects and see how they're going to interact, right? So here you can see, different kinds of behaviors. We always have one anchor object and another sort of moving object relative to them. We can also, look at the contacts being generated and, learn to predict those. But the key thing is to sort of look at how these different kinds of, pairs of objects are going to result in different effects based on which actions we apply to them. And so what we can do with this data is that we can start creating triplets of samples. So we always have an anchor object, which is going to be just some sample. And we want to identify other samples that are going to be similar to it or that are going to be very different from it. So for the similar case, we have what we call a positive sample. In this case, if we look at, here we have, two scenes. We have these two blocks that are interacting. And we have different actions. So this column is, for example, looking at the effect of moving downwards. Here we have moving to the left of the blue object, and here we have moving to the right. And so for the positive examples, we get very similar interactions. So in both cases, they're kind of just stably on top of the object. If we move to the left, they just shift to the left, move to the right, shift to the right. For the negative example, for example, even though it's still partially over this cylindrical object we have here, we actually get a very large torque. And so the effect of moving the block downward is actually going to be fairly dissimilar to what we saw for the anchor object. So this is going to be labeled as a negative sample when we want to compare them. And so ultimately, we're going to be looking at our object in terms of, or our scene in terms of voxels. So we're going to have these kinds of representations. And these two, up here are going to be considered similar, whereas this bottom one is going to be a negative dissimilar example. So given this data set of different kinds of effects of interactions between various different geometric shapes, we can start learning an embedding which will capture these various different interactions in a continuous manner. So we want to avoid sort of discretizing and sort of saying, okay, this is above, this is next to, but rather still represent them in a continuous manner if possible. So we try to avoid losing as much information. So we have two different types of losses for our network here. So here you can see this is the input to our network, actually the voxel versions of these. We're going to have our embedding network, which is going to be used to represent the relationships between the objects. Each one of these is then going to be represented as an embedding, shown here by these three blocks. We're going to have this triplet loss, which is going to try to move these the positive and the anchor objects closer together in this embedding space, while making a margin to the negative example, so pushing those further away. We're also going to be looking at using these embeddings to predict the effects. So we have our action here. We have an additional network where we're trying to predict how does this action affect the position, the orientation, and the contacts given just that embedding space. Okay. So once we have that embedding learned from simulation, so we can create large amounts of data, the next step is really to use this to learn the preconditions. And in this case, we are going to be working with real data, but because we already have very very insightful, I would say, embeddings of our object relationships, we can learn these the preconditions using very small amounts of data. So 30 samples, for example, from the real world. We used two different approaches for this. We looked at using relational neural networks, where we can sort of look at the various different relationships between the objects, sum those together and pass that through an additional network. But the one that worked really the best was using graph neural networks, where we sort of use these REL, so these embeddings as the messages that we pass between the different object nodes in order to sort of pass messages further along. And so you can imagine that if there's multiple step interactions between these objects, that the graph neural network can be quite effective. So here you can see one of the results of the experiments. So here we have a sweeping task where the robot's trying to predict whether or not all these objects are going to move if we try to sweep them with our knife. This is the input, right? So we have our different voxelized representations of our objects. We can predict which ones are going to be, we can extract the embeddings between them and then use those overall to predict whether or not they're going to be swept together. Using our approach, we get an F1 score of around 0.952 compared to a lot of the baselines, which are around 0.6 or 0.65. And one of the nice things about our approach is that it actually works quite well with different sizes. So, if we change the size of the objects between the training and the test set, often they still get mapped down to the same sort of relationships. And therefore, it's sort of robust to those kind of changes, given the fact that the interactions are still going to be similar. We also looked at another task, which was extracting objects from a block scene. In this case, we have one black object shown here. The question is, if we remove that, can we remove it without disturbing the rest of it? For us, as humans, this is a fairly simple task, but obviously, it does require considering the interactions with various objects in the scene. And again, you can see, we get a high performance in this task, even when we sort of generalize from different types of blocks at training time and at test time. And finally, starting to move in the direction of food cutting. Here we have a robot with a knife. It's going to be sort of, predicting whether this is a safe interaction. So as we can probably all guess, this is not going to be a safe interaction because the blade is kind of pointing towards another object. And again, we can sort of extract those kinds of relationships. And we can even reason about situations where, what happens if we remove one of these objects. So if we actually remove the bell pepper, we know then at that point the preconditions are fulfilled and we can actually perform the cutting task. All right, so some of the key takeaway ideas, I would say, from that part of the presentation. First of all, we should be thinking about skills and how we can sort of decompose them. We propose using object-centric task axis controllers so that we can sort of reuse these controllers between different situations and also generalize between objects much more efficiently. The other part was looking at actually representing scenes and breaking those down into individual objects and the interactions between them. Often those low-level interactions are a lot simpler, and therefore we can learn them much more efficiently using, for example, simulation. And then we sort of spare a lot of time learning all the complexity on the real system. All right, so that was sort of looking at modularity. The next part we're going to look into is how we can sort of look at defining the scope of our problems. So when and what to learn. So ideally, a robot would actually tell us when it should be using a learning approach rather than just using a planning approach, right? So planners have the benefit that they can generalize very well. They can be used in lots of different situations, but often they sort of require a very suitable model of the task in order to perform this effectively. On the other side, we have sort of learned skills, which can adapt to new situations. They don't require accurate models. They can sort of learn in a model-free manner or from demonstrations, but they do require data. And so we also want to avoid the situation where you're learning lots and lots of skills, which your planner could actually already solve for you. And so the way that we're thinking about this is to actually have the robot identify when it needs to patch a model during failure. So you can think of this as sort of a state space shown here. So I assume everyone can see my mouse, right? Yep. All right, so we have a state space where the robot's generally going to, the model is going to be accurate and we can predict exactly what's going to happen. But there's going to be some region also where the model fails. So often this will be, when we have a complicated contact interaction with our environment, and we need to adapt to that. And we may actually have our goal state sort of within that region. And so if we just use our planning approach, we're always going to end up, getting to situations where we can't use our planner because our model fails nearby and we don't know how to adapt to that. So instead, in these cases, what we're going to do is we want to learn a skill which will get us from some skill preconditions at the boundary of that area, and then actually bring us to that goal state. So what does the system look like? So we're going to start off simply going with a model-based approach. We can create a plan using a planner. Here we can see what this model looks like for this task. This is a shape insertion task, reasoning about how to actually put this square block into the square hole. We're going to be executing this. So this is at training time. We can execute it and we can detect deviations from what we expect. So at every single time step, we can see, are we performing the way that our model predicts, or are we seeing large deviations? So these could be, deviations in the positions of objects, but they can also be sort of, being in contact when we don't expect to be in contact. So here we have some examples of the kind of problems that happen when we apply this to the shape insertion. So the handle might twist, or we might get a misalignment, or we're just slightly off-centered from the location we want to be. And we can detect these during execution time. One component that we then learn is a model validity classifier. So identifying which regions of the state space do we actually succeed, and which ones do we fail, okay? So obviously, if we don't expect that we're ever going to fail, then this classifier should let us know that we don't have to worry about using a skill. But in some cases, there are going to be errors, and so we want to be able to capture that. If we do come across an error, then we're going to request a demonstration from a human. In this case, we're going to give demonstrations using a keyboard input. And that's just going to give us two things. So the skill policy, obviously how to perform the task, and also the skill preconditions. So we'll move the block to a different location where we can execute the skill policy, and that'll give us that, that orange blob here, right? So we want to create this kind of a structure here where the orange blob and the skill to go to the goal. So at test time, we now want to use our newly acquired skill. So we can again start over our model-based planning. Once we have a plan, we're going to pass that plan through our model validity classifier. That's going to allow us to detect whether or not this is going to actually work, or whether we're going to reach an area where we expect that the plan is going to fail because of modeling errors. If everything goes as expected, we just execute it, and that should work well at that point. If we predict that there is going to be an error, then we can use the learned skill preconditions to replan a path to first reach those skill preconditions and then execute the skill policy. And then that allow us to perform the insertion task successfully. So here you can see the training. So the robot's going to pick up the object. It's going to use its plan to try to get to the goal state. In this case, there's a fairly complicated interaction at the insertion. So now a human takes over, moves it to a suitable start location for the skill, and then executes or shows how to perform the insertion. At testing time, the robot's now predicted that there's going to be an error if it just directly tries to insert it. So it's again going to plan towards the preconditions of the skill, and then based on that, it's going to execute the skill to successfully insert it. So here you can see some of the results. So we compared to using only a planning-based approach. We also tried a DMP approach, which is something I've used a lot in the past, for better or worse. We can see here in blue successes, in orange we have partial successes. So this means that it reached the opening of the object, but it couldn't insert it all the way. And failures where either it didn't reach the slot at all, or it hit an obstacle along the way. So on the right here, we have with obstacles. As you can see, DMPs are not great with handling obstacles. We do have the planner works quite well with partial successes. It's that last bit of insertion that's more difficult. Where in our case with the learned skill, we get a fairly high success rate even with additional obstacle. Another thing to point out is that we do get fairly quick learning, so fairly efficient learning. So even with just one expert demonstration, we get a success rate of 7 out of 21, and this quickly goes up. So with 20 demonstrations, we get 19 out of 21. What we see here is the case where we have 10 demonstrations. I think one of the benefits of this kind of a system is that because the robot is allowed to choose when it actually learns, it can define a very narrow scope to learn from. So it's a very specialized skill, but that's also kind of what we want in this kind of insertion task. And therefore, we can learn that skill much more efficiently. So if we sort of said, okay, we want to go from further out, learn a more general skill that's going to handle a lot of the things that the planner can already do, then we're going to need more data in order to sort of handle those situations. One nice result of this project was also, we tried this on a door opening task. And in this case, the robot simply decided that it didn't need any learning. So that was also kind of a nice result. So usually, we put a lot of learning into different things, but it's good to see that the robot can sometimes say, no, it's okay, I'm fine without that. All right, so, that last project was really looking at situations where we want to use, where the robot wants to sort of say, okay, I need some additional learning here. And particularly focusing on more difficult tasks so that we collect data in the regions where we really need to learn it. Another way that we can sort of structure our approach is thinking about what to learn, right? So if we have a complicated environment, there's going to be a lot of irrelevant objects, things that we don't really need to adapt to. And what we want to do is we want to learn, or we want to acquire a policy which is largely going to ignore those irrelevant components and really focus on just the relevant features for how to adapt the behavior. So we can represent all of our different scenarios as some kind of a vector of task context. So shown here in C. And like I said, many of these are going to be irrelevant. So we can sort of think of these orange ones as the relevant variables. So if I'm cutting a cucumber, it might be the length of the knife, it might be the position of the knife, the position of the cucumber. But as long as there's a can sort of off to the side somewhere, I don't need to consider that, right? I don't need to consider the color of the cutting board either. So there's going to be a lot of irrelevant variables in there that we don't need to adapt to. So what we want to do is we want to actually determine what that structure is. So we want to be able to identify these relevant variables so that we can learn a mapping from them to our skill parameters. Okay, so these might be DMP parameters or waypoint parameters or some other form of controller for performing the task. So the second kind of mapping sort of takes, all the relevant parameters and maps them to all of the our skill parameters. We could try to go one step further, which is actually to look at which of these context variables specifically are going to map to which of these thetas. So which of these skill parameters. Now, in this case, we have ones down here, which we considered irrelevant over here, but think of all of these as being the relevant ones, and sort of finding specific mappings. So we effectively learn a separate neural network for each of our skill parameters, which is only going to depend on the variables that are considered relevant from that context. So how do we sort of determine that structure? The way that we've been looking at this is by thinking about it in kind of an intuitive physics approach, right? Often we can acquire a very simple model of the kind of task we want to perform. This might be a kinematic model or a simple simulation. And we want to be able to use that internal model in order to extract the structure, right? So here we have our source domain, which is this internal simulation. As is usual in our sim to real, we'd learn our initial weights here and then fine tune them on the target domain. In this case, what we're also doing is we're doing some causal interventions at this level in order to try to explicitly determine the network structure and which of these context variables we should actually be considering. All right, so how can we do that? So let's imagine we have a block stacking problem. So it's a fairly basic toy problem. We want to stack the red object on the blue object. This is a specific context, so we have specific object locations, specific heights of objects, and intuitively we already know that the red and the blue ones are going to be relevant. But how can we sort of determine that, right? And so what we want to do is we want to go from this situation where we have all of our context variables as input to determining which ones are actually relevant to this task. So the first thing that we do is we actually solve the task for this very specific context, right? We don't need to consider generalization at this point. We only need to figure out which thetas are actually going to allow us to perform the task. Once we've done that, we can start applying interventions. So for example, here we move this orange block to the side. Again, this is in simulation, so this is a trivial change, and we can observe the resulting performance, right? So in this case, stacking this block on this one, there's no change to the reward function. Everything is as before. And so we get the same performance, which means that moving this block in the X direction is an irrelevant feature, right? We don't have to really care about the X position of this object. By contrast, if we, for example, change the height of the blue variable, the blue blocks, in this case, we are going to get worse performance. So the task actually fails. And we can therefore infer from that that the Y height is actually relevant, okay? And so we can sort of go through all the different variables that we have and identify for each one whether these changes are actually going to affect the task performance overall. And so by doing that, we can sort of narrow down, from all of these input contexts to just the ones that are relevant. What about, going deeper than that? Can we actually identify sort of individual mappings from these context variables to the skill parameters? So to do that, we're again going to have our given context, so we can solve that one. And now what we're going to do is we're going to change a specific context variable with a delta C. So in this case, for example, we move the blue box to the side. Obviously, that's going to initially fail. But what we can do is we can again solve this problem. So in our case, we use, for example, relative entered policy search in order to resolve the task for this new updated context. And we'll have some new variables, right? So we'll have some new waypoints, for example, for the height of this, how far to move to the right, how far to move upwards. And what we can do then is we can choose, or we can go through our changes. So as we go from theta to theta dash, we can sort of look at which of these variables do we actually have to change in order to solve this problem. So for example, we move to the right further, but we also initially tried moving higher up. If we change our parameters so that the height was the same as before, we can still perform the task, right? So we want to sort of see which minimum set of changes from theta to theta dash allow us to actually still perform the task. And so in this case, the change in the X position was very important for succeeding, but the change in the Y was not important. And so we can infer through this causal intervention that this delta X, or the X variable, is relevant for the theta X skill parameter, but it's not relevant for the theta Y. Okay, so we can create this sort of partitioned network based on that sort of causal reasoning. We evaluate this on 2 tasks. So block stacking, as we just saw. Most of our evaluations so far have been in simulation. So going from a very simple sort of kinematic model to our Isaac-Jim model as our target domain. So we looked at block stacking and crate opening. So we can see here, so at the top, you can just see some examples of these environments. Down here, we have using the full context, using just the full mapping from all the relevant ones to all the skill parameters, and this partition one where we have specific context variables mapping to specific skill parameters. We have here the number of updates that we need. So for example, if there's no shift in the parameters from the model, from the internal model to the external one, we get that there's a sort of a direct zero-shot learning for the partitioned model, fairly efficient. On average, only half a policy update to relearn the one with the reduced MLP. And if we have the full one, we usually have to go for more than one policy update, often 2 or 3. If we actually do a shift in the parameters, so for example, we move the objects to the side, or we change the colors of the object, in that case, we can see a much larger improvement. So obviously the one that takes the full context, it's a much larger shift in the domain, even though a lot of that shift is irrelevant. Whereas in our case, because we've done this causal reasoning, we're only focusing on the relevant parameters. We can still, we're very robust to these kinds of irrelevant shifts, and therefore we can still learn the policies quite quickly. We also looked at this for the crate example. In this case, the RMLP, so this is the one that takes all of the relevant context parameters, maps into all the skill parameters. That one actually performed slightly better than the partition one. So it seems that with the partition, we do lose this idea of weight sharing between the different networks. And that seems to be sort of causing a decrease in performance in this case for this kind of model. Again, here we have sort of the same stiffness in our internal model and our external model, whereas here we've changed the dynamics by having a much stiffer door. And you can see that again, we get this sort of a benefit of reducing the state space or the context space for learning efficiency. We are also working on actually applying this to the real system. So these are videos I got this morning from my student. So he's currently working on applying this idea to the real robot. And we can also see here that here we have the full context variable. Oops, on the left. On the right, we have the partitioned model. And we do tend to sort of get a higher zero-shot performance already with the partition model, just because there's a lot of these sort of low-level variables that might be slightly different from the simulation to the real world, which we've learned to ignore outright, rather than trying to learn just low values for them. All right, so some takeaway ideas from the sort of the idea of scope. One of them I really think is important is this idea of focusing the learning on the parts that are really challenging. So not just trying to learn everything, but really focusing on where we can sort of narrow down on the key challenges, having the robot identify those themselves, and then learning very quickly how to actually perform those tasks. The other part is really the idea that these internal models that we have, they're often very useful, not just for directly learning the weights, but actually for structuring our problems. And I think that's going to be really one of the benefits of sort of this intuitive physics, is this idea of structuring the policy before we learn the real world. I think it's often easier to sort of say, this feature is relevant or not relevant, rather than trying to exactly predict how to use that feature. Okay, so the last part of my talk is going to be looking at interactions and how we can use interactions with different objects in order to acquire additional information for manipulation tasks. So subtitle for this one is how to get the most out of good vibrations. So whenever I think about manipulation tasks, I often think about the mode structure of manipulations. So there's a lot of inherent structure in manipulation tasks in terms of the different kinds of contact states that we have, right? So in this first example, the hand, it can't actually manipulate the object. Once we've made contact with it, we can start applying forces to it, either upwards, sideways, however we want. If we apply enough upward force, we can move the object around in free space. Whereas if we apply enough sideways force, we can actually scrape that object across the surface, right? And this, the structure is very important because it's going to capture things such as, goals and error states. So if I want to scrape across the surface, then, this becomes a sub-goal, whereas this becomes an error. Similarly, if I want to pick it up, then, maybe I want to pick it up without scraping it. So I want to go, to transition to this mode rather than this mode. Another important thing about this is that there's a lot of signals that we can use when we have mode transitions. So when we make contact with an object, when we break contact, or when we have sliding contact, all of these different kinds of interactions are going to result in vibrations, okay? So these are going to tell us, important things about, when that mode transition's happened, have we performed this correctly? So, if you're trying to pick it up and you hear a scraping sound, it probably means you're not doing a great job right now. So this is sort of a classical example from human grasping, but we can use this for other kinds of manipulations as well. So for example, here we have a robot cutting, and we have different modes. So we make contact with the side to localize it. We then want to detect when we actually make contact with the robot with the modes here. And also when we sort of, we're going through the middle of the object, and finally we scrape on the bottom of the board. So we actually looked at identifying these different kinds of mode transitions using largely just tactile vibrations, okay? So we have, you can see in the back of the knife here, a contact microphone. We also have another contact microphone over here on the tongs, and 3 underneath the cutting board. And so these, whenever we make a mode switch, so whether we're scraping on the surface, we're sliding off the vegetable, these are all going to create these sort of characteristic vibration signals, which we can detect using the microphones in order to sort of switch our controllers as needed, right? So if we directly go down and we hit the cutting board, we can detect that and avoid trying to, dull the knife by slicing across it. Similarly, if it's a smaller object, we cut through it more quickly, then we'll also be able to terminate sooner when we detect the board contact. Of course, detecting which mode we're in is just part of the signal captured in these kinds of vibrations. The other important aspect of that, and what I want to focus on here, is actually material information. So when we make contact with an object, so if I make contact, well, I can't see myself, with this glass bottle, it's very easy for me to tell whether I'm on the paper or whether I'm making contact with the glass. And a lot of that comes from the vibration signals, very small vibrations at the fingertip. And so what we wanted to do is look at actually inferring the material properties from the objects that we're cutting. Okay, so we want to identify which type of material it is based on the vibrations from simply moving the knife down and making contact there. So to do this, we collected a data set with 25 different materials. So here you can see the different kinds of vegetables and fruits that we looked at. You can see that a lot of them have visual similarities. So we have, for example, cucumber, old cucumber, and zucchini. Old cucumber, it turns out, means that it's been in the fridge for 1 week, in case you were wondering. That seems to be the standard student definition of an old cucumber. We also have things like lemons, oranges, frozen lemons, which are, again, very similar looking, but have very different properties. So in order to actually be able to classify these different materials, like I said, we're just using the vibrations from that initial contact. That's given us about a 0.1 seconds of input. We also use some force features from the arm to detect it, although most of it really is coming just from the vibrations. And in order to sort of process this data, we first extract the Mel frequency cepstrum coefficients. So this is effectively the power spectrum of the power spectrum, which sort of captures the harmonic structure. The sort of intuitive way to think about this is that it captures the timbre. So if you have a brass instrument and a woodwind instrument playing the same note, you can still tell the difference between the two instruments, and that's really because of the timbre of the sounds. And so in this case, rather than brass and woodwind, we have oranges and cucumber. We take those features, put them through a fully connected 3-layer network, so fairly simple structure, and we use that to try to predict those 25 different food classes. Here you can see the results. So we get an F1 score of 0.99. Obviously the max value is 1. We can also see here the confusion matrix. So this is only the ones with errors. So obviously a 25 by 25 would be fairly large. But for example, we can see that, the watermelon at one point, it thought it was a frozen lemon. Again, this is without any visual input. This is purely based on the vibrations. Or for example, the spaghetti squash, it thought it was a watermelon one time. But this is very promising. It's very good at identifying different types of food. And once we actually identify those, we can also start adapting our parameters, right? So in this case, we provided the robot for each one of these 25 different classes a set of parameters for a cutting skill. So here you can see it detects for different objects. So for example, the carrot tends to apply more downward force that we defined. Here it's detected as an old tomato, so there's much more back and forth movements, kiwi and cucumber. And so these are all examples of fruit and vegetables that the robot has actually encountered during the training process. And you can see that the tomato is a bit slower because it's going more back and forth, whereas the carrot is more straight down. What I find really interesting is when we apply this actually to new types of materials. So here, for example, we have a peach. The robot has never encountered a peach, but it feels very similar to a zucchini. And if you've ever sort of, played around with or interacted with a fairly unripe peach, you can see how those might have very similar properties. We have an apple here, sorry, a pear here, which it predicts as an apple. So those are obviously have very similar internal structures and are fairly similar fruits. We also have a jalapeno pepper, which is identifying again from the vibrations as a bell pepper. And so it's going to be using similar properties, sort of similar skill for this jalapeno pepper as it would for a bell pepper. So these were obviously very encouraging results. We can seem to be getting a lot of information from the sort of interactions. And so we were kind of thinking about, how can we sort of expand upon this? So we were looking at actually, learning from playing with food. We want to learn these sort of embeddings of the food items in an interactive way. Ultimately, here we have, again, different kinds of objects. We play with them. We, as a child would almost, squishing them, dropping them, listening to the vibrations, looking at how they change. We use this, again, for a learning of representation. So we still want to learn a visual representation, but using these sort of different kinds of interaction features in order to, guide that learning process. And we can actually see that, for example, if we're trying to predict juiciness, so these are human labels, but if the robot sort of plays with it, we can get a much better performance of predicting whether these are juicy or not by using representations based on the audio from the playing versus just visual features. And similarly, for the hardness, we get a benefit of playing around with the proprioception. One really nice result, this is an embedding learned from the audio from playing with the food. Here the circles are not boiled, and the same color ones in this little line shapes, these are the boiled ones. So we can see that as we boil, we get a very nice distinction between unboiled and boiled. And we actually get certain nice things like the carrots and the potatoes are sort of dissimilar to each other when they've not been boiled, but as they get boiled, they become much closer to each other in that embedding. And I think that sort of captures a kind of an intuition we also have about how these feel. All right, so make use of vibrotactile information, make use of interactions. This, there's a lot of valuable information in there. One last thing I do want to mention, we also have been working on hardware. So I've been working together with Professor Zeynep Temel on developing these sort of very dexterous delta grippers. So each finger has 3 degrees of freedom. This is very exciting research. I would definitely suggest talking to her if you want to know more about this project. And yeah, I'd like to thank all of my students who did all the hard work on these projects, as well as obviously our funding, or our sponsors. And with that, I'm at the end of my talk.
Thank you so much.
Yeah, great talk.
Any questions?
I have a question about, So I think in one of your work, you used the contrastive learning and you used the triplet loss. I'm wondering, is there any reason of using a triplet loss instead of something like the NCE loss?
Nothing explicitly. This is just kind of what we tried out, I would say. So we didn't try the other loss, and we seem to get good performance with it. So there wasn't sort of a specific target reason using one versus the other.
Okay, yeah.
I have a question on the food stuff is of course very, very cool. And so how close are we to, let's say, there's a bowl with different kinds of fruits and vegetable, and I just say, okay, I want 2 carrots sliced thinly and then a potato peeled and cubed, so that all the different pieces can just fit together, and we could do that.
I would definitely say it's a situation where the devil's in the detail. So one of the things we really came across in this project was the challenges of grasping. So obviously there's been a lot of research done in grasping and, picking up objects and, but actually holding objects so that you can cut them and then easily sort of re-grasp them, that's still very difficult. So that still requires, I would say, a lot of engineering right now for the cutting skill. The actual back and forth, I would say, is that's actually we were quite well. We recently had a project looking at reinforcement learning with that. We can learn different types of cuts, so scoring, pivoted chop, this kind of normal back and forth chop cutting. So I think we are making good progress, but I think once we actually get to the point where we're integrating these different systems, when we're thinking also about sort of transporting the food, so we can chop things up. Often things get stuck on the side of the blade. So how do we sort of remove that? I think there's a lot of those kind of nuances that are still in the way. I think the core cooking functionality, I think we're doing quite well. Another area we want to sort of look into going forward is kind of food monitoring. So cutting, you're still kind of changing the shape, but not the material properties. And so we really want to start looking into cooking as a means of manipulation, of manipulating the material properties and not just the shape of it or the locations. So I think that's another active area.
I can imagine for this kind of holding even a potato or so, right, where you would say there's nothing more trivial than picking up a potato, but then holding it tight, and with the perceptual feedback that you need to integrate into this, right, so that it kind of stays in place and things like that is, as you say, it's just very subtle, right? Like
yes, yeah. And then on top of that, like I said, the re-grasping, sort of, how do you go from, rigid grasp here to slightly rigid, shifting across, that's definitely requires a lot of dexterity, I think, as well.
Thank you so much.
Thank you. And thank you very much for joining.